Professor Belfrost's computer science class is back!
Hi, welcome back. Here's another lesson, still on digital system. This is the last lesson on digital system, and starting from next week, we'll do some exercise evaluation on our two last lesson. Two last topic. This is number system and the logic, digital logic system. Okay, so let's see. Continue for computing. Okay, so let's lesson. So, for a purpose of simplification, an economet is a convenient way of representing a Boolean function, small number up to 4, and mostly variables, and there is an array of 2 raised to the power of n squares, representing all possible combinations of values of n binary variables. And in some cases, contain certain combinations of values of variables never occur, and therefore the corresponding output never occurs, and this is referred as don't-care conditions. And for such condition, the letter D, or sometimes cross, is entered into the corresponding square of the map. Okay, and this can be treated as either 1, 0, whichever leads to the simplest expression. Okay, and we have another alternative. This is Quinn-McCluskey method. So Quinn-McCluskey method is suitable for programming on a computer give an automatic tool for producing minimized Boolean expression for a larger number of variables. Okay, and it's sometimes desirable to implement a Boolean function solely with NAND gates or solely with NOR gates. And although this may not be the minimum gate implementation, but it is the advantage of regularity, which can simplify the manufacturing process. Okay, and also we have discussed about some of electrical circuits related to the use of digital logic. The first one is a multiplexer. It connects multiple inputs to a single output, and at any time, one of the inputs is selected to be passed to the output. Multiplexers are used in digital circuits to control signal and data routing, whereas the decoder is a combinational circuit with a number of output lines, only one of which is asserted at any time dependent on the parent of the input lines. And combinational circuits are often referred to as memoryless circuits because their output depends only on their current input, and the history of prior inputs is retained. However, there is one sort of memory that's implemented by using combinational circuit, which is ROM, okay, ROM, read-only memory, read-only memory. And today's discussion will discuss about another topic. Okay, we will from combinatorial circuit, and we will explain about sequential. Okay, so what's sequential circuit? Well, combination of combinatorial circuit implement the essential function of a digital computer, right? But except for the special case of ROM, and they provide no memory state information. And elements are also essential to the operation of a digital circuit. So for later purpose, a more complex form of digital logic need to be used, which is the sequential circuit. So the current output of a sequential circuit depends not only on the current input, but also on the past history of inputs. Another and generally more useful way to view it is that the current output of a sequential circuit depends on the current input and the current state of the circuit. So the simplest form of sequential circuit is the flip-flop. So we have what we call a flip-flop, and there are a variety of flip-flops, all of which share the properties. First one is the flip-flop is a bistable device. And it means that it exists in one of two states, and in the absence of input, that remains in that state. Thus, the flip-flop can function as a one-bit memory. Second, a characteristic or property is that the flip-flop has two outputs, which are always the in complements of each other, and these are generally labeled as Q and Q naught. First, let's look at the SR let's flip-flop, or SR flip-flop for C. Okay, so here's the figure showing how to implement SR flip-flop using NOR gates. As you can see that the signal has two inputs, which is S represents that set, okay, and R stands for reset, and two outputs, which is Q and Q now, as had been described before, and consists of two NOR gates connected in a feedback range. First, let's show how this replace function is as best table. Assume that both S and R are 0 and that Q is 0, then the input to the lower NOR gate are Q equals 0 and S equals 0. Maybe you need some time before you can process this information, okay? Thus, the output means that the input through the upper NOR gate are Q dot equals 1 and R equals 0, which has the output equals 0. And thus, the state of the circuit is internally consistent and remains stable as long as uh, the things that happen, okay? And a similar line of reasoning shows that the state of Q equals 1, Q not equals 0 is also stable for R equals S equals 0. Thus, the circuit can function as a 1-bit memory. We can view the output Q as the value of the bit. The input S and R serve to write the values 1 and 0 respectively into to see this, consider the state, okay? Well, Q equals 0, Q not equals 1, S equals 0, R equals 0. Suppose that S changes to the value of 1. Now the inputs to the lower NOR gate are S equals 1 and Q equals 0. And after some time delay, then the output of the lower NOR gate will be Q not equals 0. Please pay attention to the figure below. Okay, so time delay is represented using delta T. Okay, so at point in time, input to the upper NOR gate becomes R equals 0, Q not equal to 0. And after another gate delay of delta T, output Q becomes 1. This is again steady state, and the inputs to the lower gate now is equals 1 and Q equals 1, which maintain the output Q equals 0. And as long as S equals 1, R equals 0, then the outputs will remain Q equals 1, Q not equals 0. And furthermore, if S replaces 0, then the outputs will remain unchanged. Okay, as it has been the property that has been described the first time, okay? And the R output performs the opposite function. Where R goes high or goes to 1, it forces Q to become 0 and Q naught equals 1 regardless of the previous state of Q and Q naught. Again, the time delay of 2 delta T occurs before the final state is established. So the SR latch can be defined with a table similar to a truth table called a characteristic table, which shows the next state or states of a sequential circuit as a function of current states and input. And in case of the SR latch, then the state can be defined by the value of Q. Okay, so the next also on the next slide, we'll see that table A show the resulting characteristic table of the SR latch and observe that the inputs are not allowed because this will be, I mean that there are certain inputs that are not allowed because this will produce an inconsistent output where both Q and Q naught equals 0, okay? And cable can be expressed more compactly as shown in the table B, also in the next slide. And illustration of the behavior of the SR latch is shown on table C and next slide, Joe. Yeah, please pay attention. Okay, can you see which one leads to something that is not allowed? Okay, you can see the one with hyphen. Okay, so you can assign the current inputs to be 1 1 1 1, okay, because it will create an unpredictable or chaotic output. Okay, so the only avoided one is S equals 1 and at the same time R equals, okay, the others is okay. But actually, this is when you implement this with NOR gate. When you implement this with NAND gate, then this table will change. Okay, you need to give a try by yourself. Okay. So another type is called clocked SR flip-flop. This is just the improvement. Okay. So the output of the SR latch changes after a brief time delay in response to a change in the input, and this is reverted as asynchronous operation. More typically, events in the digital computer are synchronized to a clock pulse, so the changes occur only when a clock pulse occurs. And here's the figure showing the arrangement of the clock SR flip-flop. Note that the R and S inputs are passed through the NOR gates only during the to discuss about D flip-flop, another type of flip-flop. So one trouble with SR flip-flop is that the condition R equals 1, S equals 1 must always be avoided. And on way to do this is allowed to just a single input, it's okay, but it's not um, always the case that we can obtain. So the D flip-flop can finish this problem. Okay, so figure in the next slide will shows you a gate implementation and the characteristic table of the D flip-flop. By using an inverter, then the non-clock inputs to the two AND gates are guaranteed to be opposite of each other every time. Okay, so the D flip-flop is sometimes referred to as the data flip-flop because of it is in fact storage for 1 bit of data. And the output of the D flip-flop is always equal to the most recent value applied to the input. Please see the figure. Okay, so hence it remembers and predicts the last input. And it's also referred to as the delay flip-flop because it delays a 0, 1 applied to its input for a single clock pulse. And here we can capture the logic of the D flip-flop by using the following truth table. Okay, so whenever D equals 0, then the next state will be 0, and whenever the D equals 1, then the next state will be 1. Okay, the next type of flip-flop we will discuss is called GK flip-flop. So like the SR flip-flop, it has two inputs too. However, in this case, all possible combination of input values are valid. And figure below shows a gate implementation of the JK flip-flop. Please pay attention and please distinguish between JK, D, and SR flip-flop, the configuration. Okay, so the characteristic table of JK flip-flop with the previous flip-flops are summarized and shown as you know. Maybe you need to take a screenshot to view or reviewing after the lesson done. Okay, so note that the first two combinations are the same as for the SR flip-flop, and with no input asserted, then the output is stable. And if only the J input is asserted, then the result is a cat function, causing the output to be 1. And if only the K input is asserted, then the result is a reset function, causing the output to be 0. When both J and K are 1, then the function performed is referred to as the toggle function, and the output is reversed. Thus, if Q is 1 and Q naught is 1 is applied to the JK, then Q becomes 0. Okay, as an example of the use of flip-flops, let us examine some of essential elements of the CPU, which is called the register. And as we know, a register is a digital circuit used within the CPU to store one or more bits of data. This is just general knowledge. We'll cover more about register. We will have a dedicated episode for it. Okay, so two basic types of registers are commonly used. This is parallel registers and shift register. Okay, so what is the difference? So a parallel register consists of a set of 1-bit memories that can be read or written simultaneously, and it is used to store data. So the registers that we have discussed throughout this lesson are actually parallel registers. Whereas, here is the 8-bit register illustrating the operation of parallel register using D flip-flop. So control signal labeled load, okay, controls writing into the register from signal lines D11 through D18. So these lines might be the output of multiplexers, so data from a variety of sources can be loaded into the system. And a shift register, on the other hand, accepts and or transfer information serially. Consider, for example, that the figure below, which shows a 5-bit shift register constructed from clock D flip-flop. And data are inputs only to the leftmost flip-flop. And with each clock pulse, then the data are shifted to the right one position and the rightmost bit is transferred out. A shift register can be used to interface to serial I/O devices, and in addition, they can be used within the ALU to perform logical shift and rotate functions. And this layer capacity then need to be equipped with parallel read and write circuitry as well as serial. Another useful category of sequential circuit is the counter. The counter is a resistor whose value is easily incremented by one modulo the capacity of the register. That is, after the maximum value is achieved, the next increment sets the counter value to 0. Thus, a register made up of n flip-flops can count up to 2 to the power n minus 1. An example of the counter in the CPU is a program counter. Counters can be designated as either asynchronous or synchronous, depending on the way in which they want to be operated. Asynchronous counters are relatively slow because the output of one flip-flop triggers the change in the status of the next flip-flop. In a synchronous counter, then all of the flip-flops change state at the same time. And because the latter type is much faster, it is the kind used in CPUs. However, it is useful to begin the discussion with a description of an asynchronous counter first. So what is an asynchronous counter? So an asynchronous counter is also referred to a ripple counter because the change that occurs to increment the counter start at one end and ripples through to the other end. And figure on the next slide will show you an implementation of a 4-bit counter using JK flip-flops together with a timing diagram that illustrates its behavior. So the timing diagram is idealized in that it doesn't show the propagation delay that occurs as the signals move down the series of flip-flops. And the output of the leftmost flip-flop, which is Q0, is the least significant bit. And the design could clearly be extended from an arbitrary number of bits by cascading more flip-flops. Okay, so here's the figure of the ripple or asynchronous counter and the timing diagram. So in the illustrated implementation, the counter is incremented, with each clock pulse. And the J and K inputs to each flip-flop are held at a constant 1. And this means that where there is a clock pulse, then the output of Q will be inverted, 1 to be 0 and 0 to be 1. Note that the change in the state is shown as occurring with the falling edge at the clock pulse, okay? So the falling edge, so we have two edge, rising edge and falling edge, okay? So it only occurs at the falling edge, okay? So it's called edge trigger flip-flop. And using flip-flop, they respond to the transition in clock pulse rather than the pulse itself provide better timing control in complex circuits. If one looks at patterns add up for this content, it can be seen that it cycles through 0 and 001, blah, 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 and reach 1111 and repeats again 000 and so on and so on. So this cycle keeps. So again is an electric. Okay, so again is an electronic circuit that produces an output signal. That is a simple Boolean operation. Okay, I'm sorry. This is from last lesson. I forget to erase it. Okay, so the ripple counter has the disadvantage of the delay involved in the changing value, which is proportional to the length of the counter. And to overcome this disadvantage, there's a few make use of synchronous counters in which all of the flip-flops of the counter change at the same time. So now let's discuss the design of a 3-bit synchronous counter. In doing so, we illustrate some basic concepts in the design of synchronous counter. So for a 3-bit counter, 3 flip-flops will be needed, and let us now use JK flip-flops for this example, and label the uncomplemented output of the 3 flip-flop A, B, C respectively, with C representing the least significant bit. And the first step is to construct a truth table relates to the JK input and output, which allows to design overall circuit. Okay, so here's the table shown in figure A. So the first 3 columns show the possible combinations of output A, B, and C. And Chef know how to do it, okay? I don't need to explain it for you how to erase the table. So they are in the order that they will appear as the counter is incremented. Each row lists the current value of A, B, and C, and the inputs of 3 flip-flops that will be required to reach the next value A, B, and C. Okay, so to understand the way in which the truth table of figure A is constructed, let us review about the characteristics of the table of JK flip-flop once again. So here we can see if J and K 00, then the next state is Q0, Qn I mean. If JK 01, then the next state is 0, JK 10, the next state is 1. And if it is 11, then it is just the toggle of the next state. Okay, so in this problem, the table shows the effect that J and K input have on this output. Now consider the following organization of the same information. And in this problem, we can see clearly that it provides the value of the next output when the input and the present output are known. And this is exactly the information needed to design the counter or indeed any sequential circuit. And in this problem, the table is called an excitation table. Okay, when we return to the figure A shown in the previous slide, then let's consider first row. Okay, so you want the value of A to remain 0, the value of B remain 0, and the value of C go from 0 to 1 with the next application of a clock pulse. Then the excitation table shows that to maintain an output of 0, we must have inputs of 1 and don't care for K. And to effect a transition from 0 to 1, then the inputs must be okay, this is an assignment for you. Okay, check the table before and fill on this slide. Okay, So these values are shown in the first row of the table. And by simple reasoning, then the remainder of the table can be filled. Actually, you need to understand it first how this table works. Okay? So having constructed the truth table of figure A, then we can see that it shows required value of all of the j and k inputs as function of the current values of A, B, and C. With the aid of kernel maps, we can develop Boolean expressions for these six functions, and this is shown in part B of the figure below, left side. And for example, the kernel map for the variable JA, the J input to the flip-flop that produces the A output, yields the expression. Okay, and when all six expressions are derived, then it is a straightforward matter to design the actual circuit as shown in the part C of the figure, which is on the right side, right bottom side. Okay, and thus far we have created individual gates as building blocks from which arbitrary functions can be realized, and the designer could pursue a strategy of minimizing the number of gates to be used by manipulating the corresponding Boolean expressions. And as the level of integration provided by IC increases, then other considerations apply. Early integrated circuit called SSI, it provides from 1 to 10 gates on a chip. This gates treated independently in the building block approach described so far. And here are some SSI chips examples shown in the bottom side of the slide. And now they are even more and more interconnected. So the increasing level of integration will make it possible to put more gates on the chip to make gate interconnection on the chip as well. And you see the advantage of decreased cost, decreased size, and increased speed. And the design problem arises. Okay, so for each particular logic function or set of functions, the layout of gates and connection on the chip must be designed, and the cost and time for such custom chip design is high. Thus, it becomes attractive to develop a general purpose chip that can be readily adapted to a specific purpose. And this is called a programmable logic device, PLD. So there are actually a number of different types of PLDs commercial use, and we first look at one of the simplest such device, which is called the programmable logic array (PLA), and then introduce perhaps the most important and widely used type of PLD, which is the field programmable gate array or FPGA. Okay. Okay. So here are some key features and important types you need to know. Please take a screenshot on it and review it by yourself. Okay. So first, let's discuss about PLA. What is PLA? PLA is based on the fact that any Boolean function can be expressed in the sum of product form as we have seen. And the PL consists of a regular arrangement of NOT and an OR gates on the chip. And each chip input is passed through a NOT gate so that each input and its complement are equivalent to each AND gate. And the output of each AND gate is equivalent to each OR gate, and the output of each OR gate is a chip output. So by making the appropriate connections, then the arbitrary SOP expressions can be implemented. So figure A on the next slide will show you how player A with 3 inputs, 8 gates, and 2 outputs will be done. On the left is a programmable AND array, and the AND array is programmed by a connection between any PLA input or its negation any AND gate input by connecting the corresponding lines of their point of intersection. And on the right, which is a programmable array, which involves connecting AND gate outputs or gate inputs. And most large PLAs contain several hundred gates, which is 50 to 35 inputs and 5 to 15 outputs, and the connections from the inputs to the AND gates and from the AND gates to the OR gates are not specified in the programming. Okay, so here you can see. Okay, so PLs are manufactured in different ways to allow easy programming. And the first is every possible connection is made through a fuse at every intersection point. And undesired connection can then be later removed by blowing the fuses. This type of PLA is called the field programming logic array, okay? FPLA. And after quickly, the proper connection can be made during chip fabrication by using appropriate mask. It's applied for a particular interconnection pattern, and in either case, the PLA provides a flexible and inexpensive way of implementing digital logic functions. And here's the figure based showing how to do a program PLA that will like 2 Boolean expressions. Okay, so the PLA is an example of simple PLD. And the difficulty with this kind uh, is that The structure of the programmable logic plays grows quickly in size as the number of impulses increase. And the only feasible way to provide large capacity devices based on SPLD architecture is then to integrate multiple SPLDs onto a single chip and provide interconnect to programmably connect the SPLDs blocks together. But many commercial PLD products exist on the market today with this basic structure and are collectively referred to as complex PLD or CPLD. And the most important type of CPLD is called FPGA, which has been stated before. So an FPGA consists of an array of uncommitted circuit elements called logic blocks and interconnect resources. An illustration of typical FPGA will be shown in the next slide. And the key components of FPGAs are only three. The first one is logic block, which is the configurable logic blocks are where the computation of the user's circuit takes place. The second one is I/O block, which is the I/O block connects I/O pins to the circuitry on the chip. And the third one is the interconnection. So these are the signal paths available for establishing the connections among I/O blocks and logic blocks. So here's the structure of the FPGA. This is the architecture, general depiction, and a logic block can be either a combinational circuit or a sequential system. And in a sense, the programming of a logic block is done by downloading the contents of a truth table for a logic function. So figure below shows an example of a simple logic block consisting of a D flip-flop, a 2 to 1 multiplexer, and a 16-bit lookup table. And the lookup table is a memory consisting of 16 1-bit elements, so therefore input lines are required to select one of the 16 bits. Analyzer logic blocks have larger lookup tables and multiple interconnected lookup tables, and the combinational circuit or combinational logic realized by the lookup table can be output directly or stored in the D flip-flop and output synchronously. The separate 1-bit memory controls the multiplexer to determine whether the output comes directly from the lookup table or from the flip-flop. By connecting numerous logic blocks, therefore a complex logic function can be easily implemented. Okay, so that's that for the lesson on digital logic. I know this is still not complete. Okay, please find another resources. Actually, I will post the the supplementary materials on this on our website. Okay, which is https colon forward slash science with xyz.unaux.com. You can check it later. Okay, I have not prepared it, but I will prepare it shortly. Okay, so here's a quote for you today. So Barack Obama once said that change will not come if we wait for some other president or some other time. So we are the ones we have been waiting for, and we are the change that we seek. Okay, so be the one that change. Don't wait another to create it for you. Okay, so thanks for watching. Subscribe, give a like, comment, and share to your friend. And I'll be back on every Monday. Keep watching and be thoughtful. Goodbye. See you.